All right, let's start by now going over the quiz. So the first problem is just a polynomial. Take the derivative of that. Really, this is a situation where you're using this linearity property, maybe without even hardly thinking about it. You just take the derivative of each term and combine them with a plus, minus, plus, plus, just like you see there. So the derivative of 2x cubed is 2 times 3 or 6, x to the 3 minus 1 power, which is 2. That's the power rule. Same thing with the other ones. Minus 5 times 2 is 10, x to the first. Plus the derivative of 4x is 4, and the derivative of 3 is 0. You can put a plus 0, or you can just leave it blank. Okay, so that is linearity, and the power rule is what we use there. This one is an exponential function, but it does involve a 3x in the exponent instead of just an x. So you also need the chain rule. And technically, you need the linearity to just carry the 4 along for the ride, so to speak. The answer is 4 times the derivative of e to the 3x. If you want to think of e to the 3x as being a composition, say g of h of x, then you should pick h of x to be 3x and g of x to be e to the x. You will need the derivative of both of those. H prime of x will be 3, and g prime of x will be e to the x, because the derivative of e to the x is itself. And the chain rule says you get the derivative of the outside function, plug in the inside function, times the derivative of the inside function. G prime is e to the x. If we plug h of x, 3x, into that, in place of x, we just get e to the 3x. Times h prime of x, that's times 3. The answer is 12 e to the 3x. I'd recommend starting to practice again enough that you don't have to do this stuff over here. Remember, I say, okay, here's the way I think about it. If I focus on the e to the 3x here, I say, boy, if that 3x were just an x, it would be nice and easy. It would just be e to the x. But it's not. That reminds me I need the chain rule. There is an inside function, 3x, which gets done first. You take a number x and you multiply it by 3 first before you exponentiate. So I need the chain rule. I start taking the derivative of the outside function, e to the x, which would be e to the x, but then I got to remember to plug in h of x into that, 3x in place of x. Then multiply times the derivative of that inside function. The derivative of 3x is 3. So there's the final simplified answer. And if you left it like that, that's fine. This is a product. I need the product rule. First function is e to the x. Second function is cosine of x. The derivative of the first is itself, because the derivative of e to the x is e to the x. Derivative of the first times the second function plus the first function, which is also e to the x, times the derivative of the second. Careful, the derivative of cosine is the opposite of the sine function. If you write it like this, the parentheses must be there. These here. I always put parentheses around the input for trig functions because I think it's a good idea, but technically you see a lot of books not bother with the parentheses there. However, you should put them here. That's absolutely necessary for full credit. You can leave it like this. You can also simplify. You can bring the minus sign out in front and just subtract, or you can also factor out an e to the x like this. And this would be useful for example, determining where this derivative is equal to 0. It would be when the cosine of x minus the sine of x equals 0, which occurs, for example, at pi over 4, which is 45 degrees. That would be one example of a value of x, pi over 4, where this derivative equals 0. And that's important. That's a quotient. We need the quotient rule. Remember to start with low. Low d high, the derivative of x is 1, minus high d low, the derivative of sine of x is cosine of x, over the square of what's below, sine of x quantity squared, which you can write like this. That is standard. And you can just leave it like this. And finally, down here, it's linearity, first of all. because you got a sum of things. This first thing, x to the pi power, that is a power function. The variable is in the base. So you need the power rule, bring down the pi, subtract 1 from that exponent. Pi times x to the pi minus 1. Pi to the x, however, is an exponential function. The x is in the exponent. You need a natural log of pi times pi to the x. In the case where the base is e, the natural log of e is 1. That's why e is so special. The derivative simplifies most nicely when the base is e. And that's just meant to kind of throw you off, but I did talk about it on Monday. That's just a constant. Its derivative is 0. You could put a plus 0, or you could not bother writing anything. There's no x there. It's a constant. Can I clarify anything with what I did here? All right, more derivative rules today. Some new ones that you should know for the next quiz, which will be on Friday at the start of class. Besides these new rules, I will make the problems a little harder. For example, maybe with a problem like number 2 or 3, I might also have you use the chain rule, because maybe, well, excuse me, number 3, I might make the e to the x like an e to the 2x, or an e to the negative x, or make that a cosine of 5x or something like that. So you might have to combine rules. What's the derivative of the natural log function? We haven't talked about that one yet. You might try going back to the definition of the derivative from chapter 2 as a limit. But I will tell you, without going into details, that that is not very clear what to do when you try. It technically is possible, but you need some pretty advanced techniques. So what do we do instead? We use the defining feature of the natural log function. The fact that e to the natural log of x, by definition, is x. For all x in the domain of the natural log function, which is all positive values of x. And what we do is we make an assumption that technically is an assumption that we're not going to verify. We're going to assume the natural log is a nice differentiable function, that the derivative of natural log of x exists. And therefore, we can use the chain rule to differentiate this. But if I differentiate the right side of the equation, I also have to differentiate the left side of the equation. In both cases, I have to differentiate. I'll write a d dx here to emphasize I'm going to differentiate both sides of this equation. This equation is true for all x, right? That's a defining feature of the natural log function. If this is true for all x, and if these functions are all nice and differentiable, they have derivatives, then I should be able to differentiate both sides and get to another equation that is also true when x is positive. The right side is easy to differentiate. Derivative of x with respect to x is 1. The left side, you need the chain rule. Inside function is natural log of x, whose derivative we're trying to find. Outside function is e to the x. Remember my intuitive way of thinking about the chain rule? Boy, if that were just an x up there, that problem would be easy. If this were just an x, the derivative would be e to the x. So start writing that down, start writing down e to the x, but then wait, hold your horses. It's not an x, it's a natural log of x. So put a natural log of x there. Then multiply times the derivative of the inside function. But wait a minute, I don't know the derivative of the inside function. That's what I'm trying to find. Well, that's okay. Just go ahead and write it symbolically. d dx of natural log of x, whatever that happens to be. Then you look at this equation for about 5 hours, and all of a sudden you realize, hey, I could solve this equation for the derivative I'm trying to find, couldn't I? Couldn't I just divide both sides by this? Sure. As long as I'm not dividing by 0, which I'm not, because remember my old teacher who talked like this? Yeah, yeah, e to a power is never ever 0. So there you have it. There's the derivative of the natural log function. Is that right? Can this be simplified? It simplifies to 1 over x. It is true. This is the derivative of the natural log function, 1 divided by e to the natural log of x, or if you prefer, e to the negative natural log of x. But that simplifies because once again, I can use the defining feature of the natural log function. E to the natural log of x is x when x is positive. What about when x is negative? Well, remember the natural log function in our class at least is not defined for negative numbers. Why did I say for our class? There are actually other classes where you can define it for negative numbers, strangely enough. Though when you do, you have to talk about complex numbers. So we're trying to avoid that. That's the answer for us. And this is something to memorize. The derivative of natural log of x is 1 over x when x is positive. And it should make intuitive sense when you think about the graphs. The graph of natural log of x, I hope you remember, looks about like that. You should remember that. Increasing concave down, it's got a vertical asymptote at x equals 0. Does it have a horizontal asymptote? Kind of looks like it might. I drew it like it might. But you should know it doesn't. It is going to go to infinity as x goes to infinity, though very slowly. It will eventually get above any horizontal line that you draw, no matter how high that horizontal line is. That's not obvious from the graph. The graph could be misleading you if you think that. Anyway, that's the natural log function. What does the graph of its derivative look like? The graph of 1 over x looks about like this. I'm avoiding writing y equals because, well, I don't want to confuse the issue here. This is the derivative of natural log of x. So its values, its output should give you the slope of natural log of x. And it should seem reasonable that that's the case. When x is close to 0, the value of the derivative is a very large positive number. So the slope of the purple graph is a very large positive slope, which it is. As x increases, this function goes down, it decreases. In other words, the slope of the purple graph decreases towards 0. The slope does decrease towards 0, but that does not mean it has a horizontal asymptote. That's pretty confusing, but it's true. In effect, the slope doesn't go down fast enough to make this graph have a horizontal asymptote. By the way, 1 over x at x equals 1 does have a value of 1. The slope of the natural log function at x equals 1 is 1. That's not true for logarithms of other bases.
Is 1 over x the inverse of natural log of x?
No, the inverse function of natural log of x is e to the x.
Oh, you're right.
Yep. The derivative of natural log of x is 1 over x. Interesting. The derivative of a weird non-algebraic function, the natural log of x, is a fairly simple algebraic kind of function. Question? You mean the log of some other base? Is that what you're asking? I'll talk about that on Friday if you could remind me. But I have a lot of other things to get to today. But thanks for asking. That's a good question. By the way, I don't want you to forget about antiderivatives, indefinite integrals. The indefinite integral of 1 over x, at least when x is positive, is the natural log of x plus c. Actually, this is true when x is negative as well, as long as you put absolute value signs around the x. Why? If x is negative, the natural log of the absolute value of x is actually the natural log of the opposite of x, which is a positive number when x is negative. And the derivative of this, therefore, can be found with the chain rule and what we just derived to be the inside function is negative x, the outside function is natural log of x. The derivative of natural log, we just said, was 1 over x. So I start to get 1 over x, but then I replace that x with negative x. And then I multiply times the derivative of negative x, which is negative 1. Hey, and those negative signs cancel. You get 1 over x. In other words, really, the derivative of the natural log of the absolute value of x is always equal to 1 over x as long as x is not 0. So because of that, and because with this function, it can be defined when x is negative, you put absolute value signs around the x here. And that is worth knowing, and it's sometimes helpful. Sometimes need that fact in calculus 2. Should be able to follow this. Maybe you didn't right now, but you should be able to look at this part of your notes maybe tonight and say, let me make sure I get this and check all this. Perhaps this is the most confusing part right there. Natural log of the absolute value of x equals natural log of negative x when x itself is negative. Because when x itself is negative, its opposite is positive. You are taking the log of a positive number here when x is negative. So you can use the chain rule like I did. And again, you get the same answer, 1 over x, even when x is negative, for the derivative of the natural log of the absolute value of x. Which also seems strange because the absolute value function itself is not differentiable. So you might wonder, is there a problem here because of that? But it turns out there's not. Another new derivative you should know. Are they working on the door there? Is that what they're talking? Let's do our best. What's the derivative of the inverse tangent function? We don't know yet. But just like with the log, we can derive it. How? Use the definition of the inverse tangent function as satisfying this equation. Tangent of the inverse tangent of x always equals x. This is actually true no matter what x is. This is true for all x. The inverse tangent function actually has a domain that is the entire real number line. You can plug in any number into the inverse tangent function. You can't plug in any number into the tangent function itself, like tangent of pi over 2, for example, it turns out to be undefined. But inverse tangent of x never equals pi over 2, so that's not a problem. This quantity is always between negative pi over 2 and positive pi over 2, not equaling those two numbers. You can plug in any value of x. Differentiate. I'll just draw one arrow this time. d dx. That differentiates to 1 just like before. What about this one? Well, we know from last time the derivative of tangent is secant squared. I'm using the chain rule here, so I plug in the inside function into that, and then I multiply times the derivative of that inside function, which is the derivative I'm trying to find. So I write it in the unknown form, you might say, and then I solve for it, but divide both sides by secant squared. The derivative of the inverse tangent function is 1 divided by secant squared of the inverse tangent of x. Yikes, that's kind of complicated looking. Can that be simplified? It turns out it can. One way you can simplify it is to use the fact that the secant function is 1 divided by the cosine function, and therefore 1 over the secant function is really the cosine function. And therefore 1 over secant squared is really the cosine squared function. You can write it like that. That's a little bit nicer looking. At least it's a cosine instead of a secant, and it's not a fraction anymore. But that cannot be simplified. It's still kind of a weird function. Turns out it can. This is not a proof, but it helps you think it through and derive it. Draw a right triangle and pretend that this inverse tangent of x is an angle, which you always can pretend. Pretend it's that angle, say. Inverse tangent of x. Well, why can we pretend it's an angle? Well, remember, you can take sine, cosine, and tangent of angles in right triangles. And therefore, when you take, say, inverse tangent of a number, you can think of it as an angle. That make sense? You can. You don't have to think of it as an angle, but you can. It's an angle in a right triangle. And I also think about SOHCAHTOA. I know the tangent of that angle is opposite over adjacent. But hey, opposite side over adjacent side. But hey, the tangent of that angle, I already know, it's x. There's my angle, I'm taking the tangent of it. It's x. So the ratio of the opposite to the adjacent side has to be x. So what does that mean these sides are? Well, how about x and a 1? That works. Or 2x and 2, or 3x and 3, or 4x and 4. Yeah, I might as well pick this side to be 1 and that side to be x. The tangent of this angle is opposite over adjacent, x over 1, which is x, which we're assuming is true here. We know this is true. I want to find the cosine of that angle and then square it. Cosine is adjacent over hypotenuse. Adjacent side is 1. What's the hypotenuse? I need the Pythagorean theorem. Call this, say, h for hypotenuse. The Pythagorean theorem implies that x squared plus 1 squared equals h squared. So h is the square root of 1 plus x squared. And h, well, okay, I didn't have to do that. H squared is 1 plus x squared. And that is the, thinking about the cosine being adjacent over hypotenuse, that's going to be the denominator of the fraction adjacent over hypotenuse. Cosine of inverse tangent of x, quantity squared. The cosine of that, again, is adjacent over hypotenuse for this triangle. 1 divided by h, 1 divided by this. But I'm squaring that so I can get rid of the square root. I get 1 over 1 plus x squared. And that's true for all x. That is the derivative of the inverse tangent function. That's something to memorize too. Both for quizzes starting on Friday and for the gateway. And for exam too, for that matter, it's probably worth memorizing, even though you can use a note card. We could keep going. What about the derivative of the inverse sine function? We'd want to use this property. Sine of inverse sine of x is x. However, it is trickier. This is only true when x is strictly between -1 and 1. Or possibly equaling the endpoints for when this algebraic equation is true. It turns out, I'm not going to show you the details, that the derivative of the inverse sine function can be derived in the exact same kind of way we did for the inverse tangent function, using a right triangle to help us again. And it turns out to equal 1 divided by square root of 1 minus x squared. But there's a problem here. If x is plus or minus 1, we'd have 1 minus 1 squared in the bottom. We'd have a 0. We'd be dividing by 0. So even though this algebra equation is true even at the endpoints, this equation turns out to not be true at the endpoints. You need strict inequalities there. What is happening geometrically to cause that to happen, so to speak? It's the fact that the graph of the inverse sine function, it looks about like this. And I'd encourage you to check this on your calculator. it turns out to essentially have vertical tangents at the endpoints. Infinite slope, you might say. And yeah, that means the function is not differentiable at the endpoints. Remember, when we do the derivation, we're kind of implicitly assuming differentiability. But it turns out this one's not differentiable at the endpoints, -1 and +1, because essentially you've got vertical tangent lines there. Also, make sure you know for the quizzes and the gateway that these notations for inverse tangent and inverse sine are not the only way to write these functions. Inverse tangent can be written as arctangent. It's the same function, just different notation. So we can also write this, and inverse sine can also be written as arcsine. So we can write this. Again, this one's true for all x. This one's true when x is strictly between -1 and 1. Can I clarify anything there? Should you be able to do these kind of derivations on the test? Yes, you should be able to. I'm telling you right now. Even if I don't assign a homework problem like these, you should be able to do these. And by the way, like I promised, so I'm going to give you information about the project starting probably this afternoon. And for starting the homework due Friday, the assignments will be shorter in terms of number of problems. I might assign harder problems, but there will definitely be fewer of them. Okay. I make them more focused on the word problems. Maybe, I don't know, maybe a few calculation problems and a few word problems, something like that per assignment. I'm not guaranteeing exact numbers. I'm just saying that kind of ballpark. I'll give you other problems too that you can do if you want more practice. I'll make them be odd problems that you can check your answers in the book, back to the book, but I'm not going to collect those other problems. It's up to you how many you do. So to give you some space for the project, as well as studying for these quizzes in the gateway. All right, so things to memorize. These things. What about the derivative of inverse cosine? I'm not going to talk about what that one today. That'll be on Friday. What I'd like to do for our last 15 minutes of class is talk about a little bit with multivariable calculus, and also at the same time section 3.7. Now, if you continue in your math education, you wouldn't get to multivariable calculus until after calculus 2. However, in calculus 2, we do make a habit of doing some multivariable calculus as part of that course. So I think it's good to introduce it a little bit here in Calc 1. And in the big scheme of things, multivariable calculus is really even more useful than ordinary calculus. So I think it's worth introducing. I don't go real heavy on it, but let's introduce it. Let's introduce it in the context of a problem here from section 3.7. Sorry, it's blurry here. Let's take a look at this problem here. 25. It says find the slope of the tangent to the curve at the point specified. I'm in section 3.7, it's page 164. X cubed plus 5x squared times y plus 2y squared equals 4y plus 11 at the point 1, 2. We write that equation down. Section 3.7, number 25 is what this is. We've got an equation, x cubed plus 5x squared times y plus 2y squared equals 4y plus 11. Again, the problem says, find the slope of the tangent line to the graph of this equation at the point 1, 2. You might write that as find dy dx at the point x comma y equals 1 comma 2. So at first, when you look at this, you might say, I guess I just need to take the derivative and plug in x equals 1. However, there's a problem. What's the function? Shouldn't I solve for y as a function of x? You could here, you could do that. It's a quadratic equation in y. You could use the quadratic formula to solve for y as a function of x and then differentiate that function. However, if the y squared, for example, right here was a y cubed, well, technically you could solve such an equation for y as well, but it's super duper complicated. And if it was a y to the fifth, there you'd have pretty much no chance of solving it for y as a function of x. Seriously, you'd have pretty much no chance. Unless this is a very unique kind of problem. So what we'd like to do is we'd like to solve for this derivative without actually solving for y in this equation, without actually finding the function. How? What should you do? This is called implicit differentiation. Implicit differentiation is what we're going to use. This equation, we say, I'm not going to write this down, but we say it implicitly, as opposed to explicitly, defines y as a function of x. But if we tried solving for y as a function of x, we'd have to use the quadratic formula. It would be very complicated looking. And again, if this was like a y to the fifth, we wouldn't have a chance of doing it. But it's still, this implicit definition still holds. I can still find derivatives of y with respect to x in this context, but I have to be extra careful how I do it. Listen really carefully. This is difficult for most people. What I'm going to do is I'm going to go ahead and differentiate both sides with respect to x, assuming, making another assumption here, assuming y depends on x. Assuming that. That's a very important thing to realize. Y is not a constant. It does depend on x. I need to treat it as a function of x, even though you don't see an f of x in there anywhere. I could put an f of x in there in place of each y, but you don't have to. Differentiate everything with respect to x. Well, that one's easy, 3x squared. But what about this one? Remember, y is not a constant here. The answer is not 10y times x to the first power. That's not the right thing to do, because I'm assuming y is a function of x, and it turns out that is a good assumption to make. You need the product rule. Say, this is the first function, 5x squared, and this is the second function, y. The product rule says to take the derivative of the first function, 5x squared, with respect to x, that's 10x, times the second function, which is just a y. But y does depend on x. Remember that in your mind here. Then plus the first function, 5x squared, times the derivative of the second. What's the derivative of y with respect to x? Careful, it's not 1. It's not 0. Are you having technical difficulties, or is it okay? Okay. It's dy dx. We can't write a formula for it, so just write the symbol. This is analogous to what we were doing with the logarithm and the arctangent, inverse tangent, in that we didn't know initially what the derivative of natural log of x was, and we also didn't know what the derivative of inverse tangent was, but we pretended they existed, and we just wrote them as ddx of natural log of x and ddx of inverse tangent of x. We don't know what y is as a function of x, so we can't write a formula there. We can only write the symbol for the derivative. By the way, it is okay to write a y prime here if you prefer, but I try to stick with the Leibniz notation. What about this one? Differentiate that with respect to x. The answer is not 4y. It's also not 0. Then what is it? It's 4y times dy dx. Why? Pun intended. Why? Because y is a function of x. This is really analogous to a 2 times f of x quantity squared if you pretend the function's name is f. The inside function here is the f of x. The outside function is 2x squared. You would need the chain rule to differentiate this with respect to x. If you took d dx here, you'd write it as 4 times f of x to the first power times by the chain rule f prime of x, the derivative of the inside function. But remember, y equals f of x. These two expressions are the same thing. These are the same, just different symbols. Feeling confused? If you are, you're not alone. Plenty of people feel confused about this the first time they see it. You got to think real clearly, exactly in the ways that I'm telling you to. What about the right-hand side? Derivative of 4y with respect to x is 4 times dy dx. Derivative of 11, well, 11 really is a constant. That derivative is 0. What do I do with this? Solve for dy dx. That's what I'm trying to do. I'm going to subtract this from both sides, and I'm also going to subtract these things from both sides. And I'm going to skip a step or two here. For the sake of time, you should fill in the missing step here. I'm missing a couple steps. This is a product here. Dy dx times this thing. I factored out a dy dx out of these, and after subtracting this over as well to get this, and I brought these over to the other sides with minus signs. Now just divide both sides by this expression here. Dy dx equals negative 3x squared minus 10xy over 5x squared plus 4y minus 4. Is this okay? Is that the answer? Well, that is the derivative of y with respect to x in terms of both x and y. But wait a minute, shouldn't it only involve an x? Well, it would if you solved this equation for y and plugged it in there and there. Then it would just depend on x. But remember, that would be a real big pain, so we don't have to. We can just use the fact that when x is 1, y is 2, and you could double check, by the way, that this point does satisfy this equation. 1 cubed plus 5 times 1 squared times 2 is 1 plus 10 is 11. That's 2 squared times 2 is 8. 19 on this side when you plug the point in, and also 19 on this side when you plug the point in. This point is on the graph of this equation. It does satisfy it. That was assumed, really, but it's good to check. Hang on here, pretty important stuff left. Go ahead and now evaluate this at the point 1, 2. We could use the vertical line symbol if you like. 1, 2. If you do so, you get negative 3 times 1 squared minus 10 times 1 times 2 all over 5 times 1 squared plus 4 times 2 minus 4. Plugging in x equals 1, y equals 2. Hopefully I'm not making any mistakes. This simplifies to negative 23 on the top and the bottom. Try to catch any mistakes I might make. Looks like it simplifies to 9. Negative 23 nines if I've not made a mistake, which is negative 2 and 5 ninths. Negative 2.5 repeating technically is what the slope of the tangent line is. And you could then find the equation of the tangent line using this point. The equation of the tangent line would be y minus 2 equals negative 23 ninths times x minus 1. Where did I get that? The slope is negative 23 ninths. That goes there. I'm using point slope form. The 2 and the 1 come from the point itself. X is 1, y is 2. We could solve this for y as a function of x. That is the equation of the tangent line. You could also expand it out into slope-intercept form if you like. Give me 3 minutes here. We've got 3 minutes. I wanted to talk about multivariable calculus still. Well, this would be a very, very brief introduction to multivariable calculus. What I'm going to do is I'm going to define a function of 2 variables, f of x, comma y. By the way, you do not need to bother opening your Mathematica here. I will put this on Moodle. How are we doing? Tech fine? Hang with me. This is really important. 3 minutes. Plug in the original functions, left-hand side at least, x cubed plus 5x squared times y. Here I'm really thinking of y as not necessarily a function of x, which probably seems confusing. Why would I do that since before I was thinking of it as a function of x? I'm going to take the right-hand side and subtract just the 4y from it. Why not the 11? I'll come to that. This is a function of two independent variables, a multivariable calculus function. There are lots of ways to think about such functions. One way to think about them, to graph them, so to speak, is to make what's called a contour map. In Mathematica, that can be done like this. ContourPlot. And whoa, we get a kind of a weird looking graph here. What in the world? What does this represent? Listen carefully. Talk about this more on Friday. Each one of these curves that you see is called a level curve of this function. What that means is, like if I hover over one of them like this one, it says 5.4. What it means is this function equals 5.4 for points along this curve. When you plug in any point along this curve into this function in place of x and y, you'll get 5.4 out. Does this ever equal 11? Yeah, pretty close right there. Not exactly. This curve right here that you see, the output of this function is very close to 11. Why am I picking on 11? Because that was on the right-hand side of the original equation. This curve is very close to the curve defined by the equation that I just did the implicit differentiation for, with had the 11 on this side. Notice the point 1, 2 is, well, at least close to being on this curve. X is 1, y is 2, would be around, right around here, somewhere close to there. And notice the slope is negative and maybe close to negative 3, or maybe close to negative 2.5. That's what we were doing, is we were finding the slope of a curve, what's called a level curve of a multivariable calculus function, when the output is assumed to be 11 in this case. That may have been confusing. We'll talk more about it on Friday. Have a good day.